we're going live.
Okay.
So hopefully good. So hopefully now we can see the number of participants joining us on the call. To those of you out there, we've got about 5 minutes before we start today's presentation. Welcome to TMS Tuesday and TMS Training Solutions. You can see us, the panel on the right hand, hopefully on your screen now. You can see Keith, who will be hosting today, who's be hosting the main part of the presentation today, with co-hosts Rob and Paul Smith to my right. That's Paul Smith.
Hi.
And Tony Smith will be sharing his expert knowledge and understanding as part of the panel Q&A session, which will start at around about hopefully about 22. We're trying to make more time for your questions today because there are a lot of them, I know. So we're looking to have we already have quite a few. So we're looking to fit in all of your questions as much as possible within the hour today, because I appreciate some of you have other commitments, and it must be very frustrating if we don't get to your questions in the allotted time. We've had another busy week in TMS Training Solutions. Keith is planning his first. Traditionally, we provide AGL and ground traffic GTM ground traffic management training in person at designated centres across the world. Many of you I know have been trained by Keith in the past. But unfortunately, current circumstances don't allow us to travel. So Keith will be, as very kindly agreed to put together a web-based interactive training session. We're not just filming and putting videos of Keith on the screen. We're actually looking to make it as real life as possible. So we're going to be hosting, using the wonders of this modern technology, to provide you with online training covering the AGL and ground traffic management syllabus that we would normally present in person across 10 or 12 weeks, 1 hour sessions. When I say 10 or 12 sessions, which will be hosted 2 a week with a morning and afternoon for each, and a recording if you're unable to make one of those. So you'll be able to cover the course over a period of about 6 weeks. It will qualify for around about 18 hours of continual professional development for those of you that need the CPD hours, and we will be providing certificates of completion and competency for those that take the test and able to pass the test at the end of the trainings that we're providing. So that's coming up, and there'll be more information released on our website and via email to you directly in the coming weeks. But for now, it's all free as usual. Today we're talking about airfield ground lighting as a specific subject, and the webinar is due to start in 2 minutes. But I better wait for the rest of the attendees to come online, although I can see there are a large number of you there already. Keith, how's your lockdown been? You busy?
Well, actually, it's not really affecting me too much at all, because I've been able to get out and take my little dog for a walk. So that's been quite good.
For those of you who've been participating in the webinars in recent weeks, you'll have noticed Keith's dog participating actively in the Q&A session, and we almost was and Buddy, which is Keith's dog's name, was in the verge of being promoted to panelist this week by virtue of its vocal contributions to previous webinars. So hopefully we'll see something of Buddy later in the webinar. Tony, how's your week been? Hello, Tony.
It's amazing, really. The weeks seem to go past very quickly. It doesn't seem a week since we were doing this sort of thing again. Different days of the week, I have different focuses, different things I'm doing, but the week seems to go, it's going very quickly. It doesn't actually, it doesn't. I can't believe the lockdown's been so many months. It doesn't seem long since it was March, um, and I think that's a blessing, really. It's time isn't sort of hanging long and slow. Being retired, though, I'm fortunate. I don't have to worry about earning an income and all those things that many other people have got. It's quite pleasant in a strange sort of way, except I can't meet up with my friends and can't see my family and give them a good hug. But in many ways, slowing down has been quite nice.
Yes, you make a good point there about the effects of the lockdown. I know there are extensive cost reduction efforts going on across our airports around the world, and it is very, very concerning because being involved, primarily in safety and compliance, the loss of scarce resource and very often experienced resource is of grave concern, because it's at the end of the day. We're losing a lot of competent people from the industry. So I am writing personally to some regulators to try and encourage, some reinforcement of the need for, let's say, diligence in terms of ensuring that we can't relax safety because of economic constraints. It's too risky, as they say. If you think safety is expensive, try an accident. So that's something that we're doing, which hopefully in some small way will help you out there. But it is a concern. Right. Well, I think now we're just it's 2 o'clock. So I'd like to welcome you once again to TMS Tuesday. Today the subject is airfield ground lighting. We're looking at the requirements in terms of safety and regulatory requirements, and the main causes of issues with AGL. And who better to start us off today than Keith Costill, well known to you, expert and director of TMS Training Solutions, who will start today's presentation. So if the other participants, we can switch off our visuals. We'll leave the stage to Keith. Over to you, Keith.
Yes, good afternoon. Can you hear me, everybody?
Yep.
Okay. Well, say good afternoon here in Europe, good morning or good evening, wherever you are in the world. And so I would just like to say that, as Robert has said, it's all about serviceability, AGL, airfield ground lighting, serviceability and compliance this week. And some of the issues associated with that, leading on to the elements of how we manage the AGL as an asset. Here is a slide just giving us, letting you know who those persons are. Robert, you've listened to as the moderator, myself as the principal presenter, and I will be introducing Rob Billingham and Paul Smith, who are co-presenters today. And of course, you've also from last week, Tony Smith, who is the designer and an expert in many things AGL, but the design particularly of battery. So let's look at the subjects that we're covering. I'm going to have quite a relatively short session before I hand over to Rob and to Paul. We'll look at the requirements for achieving the compliant AGL and introduce ourselves to some of the photometric testing elements and how we can achieve an effective AGL maintenance as such, which will then lead us on to the asset management system of today, because this is developed beyond all comprehension from the early days of AGL asset management, and it is very data orientated now, and as I said here, data analysis in the modern era, because it is the modern era. And then talk a little bit about condition-based maintenance, which ICAO call differential maintenance in accordance with the Aerodrome Design Manual, Part 4, and there's a whole section of it in Chapter 17. So, with further ado, let's move on quite quickly. let's remember, every flight starts and ends at an aerodrome, hopefully. Right? That's what we want. And AGL is designed to support safe and regular aircraft operations by providing essential and clear and concise visual cues to the pilot, etc. And particularly important when visibility is reduced. And I'd just like to have a quick look at the dangers of underperforming AGL and look at the risk factor. The risk factor to the aviators. As the RVR comes down, the runway visual range comes down, the visibility comes down, the risk factor goes up. And you'll see this by this exponential curve. But the issue is what creates underperforming AGL? There are various factors. There's an electrical factor. Why? Because it's a light unit, and a light unit needs electrical power. We do not get the correct electrical power to the light unit, we've got a problem. There's an optical issue, the photometric side, the output. I mean, for example, and you will look today, like rubber being burnt off the aircraft tires onto an inset light in a touchdown zone or a runway center line. It's an optical issue. There are issues like with tungsten halogen lamps and things like that. There's a mechanical issue. What if an inset light? What if it comes loose and it starts to move around? And potentially, of course, a bolt coming out of an inset light would be disastrous. But the movement, that side, and also the civil. And some people tend to forget the civil end aspect because payment over time does move. And it may move to the left or to the right and stay deflected like that. So it means that our base unit, say, for example, of an inset light, is fixed with a bolt or bolts into a base unit. If the base unit moves, the light's pointing in the wrong direction, we do not get the light output. It's as simple as that. So let's just have a look at what happens in low visibility. I've just got to put a few little slides up here. You know, in fact, when you're coming into land in lower visibility, you're approaching, and eventually you will see, in low visibility, the approach lights. And then progressively, you'll see more lights. You'll see the lights before you see anything else as a pilot. But as the visibility decreases, and let's start off really with this one, and this is around 600 meters visibility, approximately, that kind of distance. And if we see a center line and there's some runway edge lights, so that's probably what a pilot will see in lowish visibility. And that is category 1, that picture, but very, very close to moving into the category 2, below 550 meters. As the visibility drops further, then we lose the lights in the distance. So the pilot will only see something like that, and around 200 meters. This is now Cat 3, you know, and if you're traveling at 200 kilometers an hour, that's around 55 meters a second, something like that. 55 meters a second, and you can only see this amount of light, then, you know, it's difficult. Hence why category 3 are principal instrument landings. And getting worse if we're down at the lower end of the category 3. So we go, remember, we have category 3A, category 3B, category 3C. And if we're at the lower end of the visibility, about all the pilot will see at 55 meters a second, 200 kilometers an hour, it's the blink of an eye, eh? And that's why it's really important that we've got visual aids to supplement in an approach and in landing, to supplement the electronic aids which enable a pilot to land in instrument flight rules. So the main issue associated with light output, let's just put them into 5. I've put them here into 5 bullet points, really. The beam intensity, the average beam intensity, and we look at Annex 14, Volume 1 for that, and there's some Iso-candela diagrams in there, which I'm going to show, which help us understand that. But the shape also of the beam and the size of the beam, now every single light unit in a system, every system has its own Iso-candela diagram, and we have to point them in the correct direction. So beam alignment is very, very important. We also have we have to have some kind of uniformity. It's no point having a hot spot down in the left-hand corner of a beam. You know, we have to have some uniformity. And of course, in AGL, we use color, eh? We use color. We need to define, the lights need to show the correct color. And one of the issues that we have in our industry, over time, if there is poor maintenance, for example, or a deterioration of the optics, etc., white starts to look yellow. And so color is an important factor. And here is the pictures of what we call an Iso-candela diagram. These are taken directly out of ICAO Annex 14, Volume 1, whole set of Iso-candela diagrams, but there's two types. And people often ask me that, well, look, some look like circles, Keith, and others look like rectangles. Yeah, they do. But really, it's really for us to be able to differentiate between runway-related lighting and taxiway-related lighting. Doesn't mean to say the taxiway lighting is square. So just to ensure that. But the Iso-candela diagram gives us a lot of information. It gives us a diagram, and there's 3 ellipses. We, in an airport, are only really interested in the inner ellipse. And during today, the other guys will explain a little bit more about that inner ellipse. But there is also a set of notes. So if there's some criteria associated with what is called towing, that means like a runway edge light on both sides of the runway at equal and opposite sides of the runway, then both of those lights will be towed in towards the center line of the runway, as an example. And if there is towing, then it will be in the notes. It is not shown in the Iso-candela diagram because the ellipses are always shown around the 0. So we go to the left and to the right, as you'll see in this Iso-candela diagram here. But so if there's towing, there will be something in the notes. And this is for a runway center line. So is there anything about towing for a center line? No, there is not. Therefore, center line are parallel with the center line of the runway. Pretty obvious anyway, isn't it? Okay. So moving on, let's have a look at that inner ellipse. And this is really, really important because on the inner ellipse, when we measure and want to get the average beam intensity, there is a set of grids in the Iso-candela diagram, one degree grids. And the guys are going to look at this a little bit later. But when we look at this grid, and this is a runway center line, the inner ellipse of a runway center line, and on this 1 degree grid, there's 52 measurement positions at the crossover points, 52. And therefore, what we do to get the average, we take the photometric calculation of every single point, add them all together and divide by the number of points. So we divide by the number of 52 in this case. Now the issue is, and what I want you to bring to your attention, if you've got rubber filled up at the bottom of the light fixture and you take away that bottom row, that is 1, 2, 3, 4, 5, 6, 7, 8 photometric points. 8 52s as a percentage is around 15%. And if we took out the second row, that would be 17 points, 17 52ths worth. As a percentage is nearly 33% of your light you have lost. And it's 33% of your light loss is already needing maintenance. So I just want to bring that into your thinking. at this time. But the guys will look at that a little bit clearer and more explanation a little later. So when we're looking at light output, we're talking candela, or candela, as some people call it. And the measurement of candela, we have different levels depending on the system. We have an approach system, and then we have the runway related system, and I've just shown 3 here. So, and principally because generally speaking, they're all white light. We know there are, in an edge light, they are yellow towards the end. We know that on a center line, they go red, white, and then red towards the end. But the approach lights, with the normal approach lights, with the exception of the supplementary or the side row barrettes, are all white. So this is white light. And when we're looking at white light, approach system is 20,000 candela. And an edge system is 10,000 candela. And a center line is 5,000. Well, that also means that as a pilot is approaching the runway, then you can see he's looking directly at those approach lights. He's got 20,000 candela. But as he approaches the threshold and he gets into the runway, then the lights are more in his peripheral vision. There's a lot of other things going on. So the ratios are important between those. And that's why we've got those different levels of light output. But each one, if I say what light output at 6.6 amps is for an approach light, I say 20,000 candela at 6.6 amps, that's 100%. If it's a runway edge light, I say, okay, at 6.6 amps, that's 10,000 candela, that's 100%. And likewise for a center line. A center line at 6.6 amps, maximum candela is 5,000, 100%. So we use that percentage as a reference point. So looking at that percentage of 100%, and there's a little diagram here where I show 2 parts. There's the serviceable side, that is above 50%, because ICAO define a light to be unserviceable when it falls to 50% or below its design. And the design, we base it on 100%. So below 50% is unserviceable, above 50% is serviceable. But we do not in maintenance wait until it becomes unserviceable before we do maintenance. So we've also brought in another percentage, which is the recommended percentage, where we start to do maintenance, that we service those lights before they become unserviceable. And that's the criteria that we adopt in photometric testing and generally. And if you look at, as I said earlier, the Aerodrome Design Manual, Part 4, Chapter 17, there's a whole section on this. So how do we actually show it? Well, I've mentioned the 50%, I've mentioned the 70%, and I've mentioned the 100%. So one of the best ways and the simplest ways to show it is in a bar chart. The other guys are going to show you more in-depth way of looking at it, but as a bar chart. And here, look, I'm showing an absolute wonderful system, really. They're all greens, so green is above 70%. But there's a couple of blues and a red. Blue is between 50 and 70% output, and red is 50% or below. So there's a pretty capture snapshot view of a typical, and this, I'm just using the center line once again as an example. Moving on, we also talk about a system. So I've spoken about an individual light up to now. So an individual light, 100% at 6.6 amps, falls to 70%, needs maintenance, 50% unserviceable. But when I put those lights into a system, then there's some generic ways of looking at it as a system. Because if I took a runway edge lighting system, then, and a runway edge lighting system in category 1 operations, then 85% of those lights need to be serviceable and no 2 adjacent lights. If I took that same system in a category 2 and a category 3 operational scenario, 95% of those lights must be serviceable. So we also got a different way of looking at individual light and as a system. And we can demonstrate that if you do photometric testing. So how do we look at a light? Well, if you're a human being, we know we've got light intensities. We've got normally 5 steps of light intensities for a runway-related lighting system and 3 steps generically for a taxiway lighting system. But step 5, in the international theatre, step 5 is 100% and step 4 is 30%. Now, a human being can pretty much not see the difference, especially under lower visibility conditions. And this is a typical example, because what happens, the light diffracts. And you know when you're driving the car and you're driving through mist and fog and your headlights reflect back at you. The same scenario, it diffracts out. So, you know, a visual inspection might be good to say, oh, that light's out, or that one looks dimmer than that one, because we are reasonably good at comparing one to another, but we can't actually measure light output as a human being. That's why we do photometric testing. And in photometric testing, I've mentioned before, Aerodrome Design Manual Part 4, there's 2 snapshots on the left-hand side of the screen here. Chapter 17, look at the back page, and there is a typical and an accurate, a repeatable, a fast to use and easy to use tool. Now that was taken quite a few years ago. The modern one looks very similar, but of course there's a lot of technology advances since the early days. And so when we're looking at using photometric testing and other elements to look at maintenance and the effectiveness of AGL, we've actually got a bit of a cycle here, because the reality is you cannot manage that you do not measure. It's as simple as that. So we do have a cycle. We measure it. We maintain from the results we found. We continually monitor, which enables us to manage, and that cycle continues. And that's what we're going to, look at today. So what kind of cycle is it of inspections and maintenance we do? Now, I'm not going to go through too much of this here, because you're going to be able to get this, presentation that you can download. But I've split it into Cat 1 and Cat 2, 3, and I've just chosen 3 runway lights. And very generically, in Cat 1, we need to achieve 85%. So if you've got, say, an edge lighting system, probably for Category 1, you need to be doing maintenance on it probably every 3 months, 12 weeks. But if there's high traffic density, you may you may have to do it every 6 weeks. And if it's low traffic density, you may be able to do it every 24 weeks. Only if you are managing, so you're measuring, monitoring, can you make this decision. So these are just an example, not fixed in stone. Don't believe, oh, Keith said this. It's about measuring, monitoring, maintaining, monitoring, assessing and making these decisions. So I'm moving on from there. And so I mentioned earlier, but I'll mention it again, some criteria associated. Why do we get such a variation in performance? Electrical, optical, or civil and mechanical, and of course the light fixture. Out there's a lot of you got tungsten halogen, and a lot of you got LEDs. Different criteria is involved now between the 2 technologies, but the concept is still the same. And so, really summarizing, I'm really coming to a summarizing now. When I look at the life cycle of AGL, right from the conceptual design, detail design, manufacture, delivery, installation, and then we're into commissioning. Is it fit for purpose? And so we need to be looking at the tools to be able to demonstrate that, and onwards through maintenance. So have a look at this, because it's a quite a good slide to bring it into bring asset management into your thing. So what I'm going to do is hand over now very quickly to the other guys, to Rob and to Paul, and Robert, as the moderator, would you like now to go over?
Yes, we're just changing over to the other presentation. And Rob, are you ready to go?
Yes, thank you, Robert.
Good. Hopefully I can maneuver that out of the way. Right. Okay, over to you, Rob.
Thank you. Thank you, Keith. Good afternoon, everyone. I'd like to talk to you this afternoon about the MALMS and MALMS engineer systems and our dashboard and the tools that are available to prove compliance and to monitor serviceability. So next slide, please, Robert. Okay, so within our dashboard, which we saw a couple of weeks ago on one of our webinars, one of the main panels is the runway serviceability. So this shows results from photometric surveys of each of your runways. So we break the runways down into runway directions. And we're showing a serviceability over a 180-day period, but this is configurable, as much of our system is. But this is a recommended period. And for each runway direction, we show a result, a simple tick or cross. So unserviceable, a tick. We also show a current status with it, which can be Cat 1, 2, 3 or Cat 1, depending on the results achieved. So these results get uploaded right away from your tablet in the field following a photometric survey. As well as the tick and the cross, we also have there's a warning badge here you see on the first runway. And this means that this particular runway has failed due to adjacent lamp failure. Now, whatever percentages you achieve on each of your services, adjacent lamp failure will give you an instant failure on that runway. It's defined by ICAO. We'll see that shortly. Also showed that the date of the last inspection on each runway. And we've got two icons to drill down into runway serviceability and straight into course bar chart. So start off with, we'll click on runway serviceability. So that brings up a bar chart. So there's a single page for each runway direction in the report. Each bar of the bar chart represents a service. So we've got centerline, edges, TDZ, threshold, and runway end. So each service could be more than one course within the MALMS system. So centerline is just one course, edges is 2, TDZ is multiple courses. So the percentage shown here is the percentage of lights which are above 50% of standard. So to get a green bar for a centerline, we need to be over 95% to be serviceable. If we achieve between 85 and 95, we'd have an olive bar, which is not shown here, but that would only leave our runway Cat 1 compliant only. But below 85%, we would have a red bar. Now here on the edge, we can see we're 86%, so by rights this should be olive in colour, but we can see adjacent lamp failure. Somewhere on this edge, there are two lights out together, which gives us a failure condition. So if we would need to investigate that, we'd click on this red bar and drill down now into course bar charts. Okay, so this is a staple report as used by moderators and engineers alike. So each bar represents a single lamp within the course on the runway. So here we're looking at the edge port course. So a green bar represents a lamp which is over 70%. So between 50 and 70, we have a blue bar, so that's a lamp that may need some maintenance. And then below 50%, the red bars, lamps definitely need maintenance. And we can see here our adjacent failure condition. We've got two lamps out there together and a bit further down the runway. The pass-fail levels, 50 and 70% are shown there. And we'll discuss this a little bit more later. The 50% is defined by ICAO. The 70%, this is user configurable, and you could even raise the bar, and lots of airports do. We might up this to 80%. You'd have more blue bars, but that would help you achieve even better compliance. Along the bottom there, you can see the lamp colours shown along the x-axis. So we've got 4 reds, the whites, and then the yellows. So now, if we wanted to look at this adjacent failure area here, we click again and drill down into Iso-candela diagrams. Okay, so on this report, we show both sides of the lamp. So on the left is the side that you've come from the course bar chart, and on the right is the reverse side. We can see the reason for failure in red. So if either side is below 50%, the percentage and the candela value achieved is shown there. And again, on the previous survey, which is shown on the row below, we can see last time it achieved a blue score, which is between 50 and 70. This report is multiple pages, so you could go back in time and look at previous surveys and see how it's achieved in the past. So I'm going to hand over to Paul shortly, and he's going to talk some more about iso-candelas and what they mean. How do I know?
Hey, thank you, Rob. Thank you, Keith, for the excellent introduction as well. So I think basically what we'll do now is talk about our version of an Iso-candela picture and how that is interpreted so that you can see what's going on. The elliptical regions that you see on here are the inner ellipse, as Keith explained from the ICAO Annex 14 manual. So we just draw those on the screen for reference. That's where ideally we want our main part of the beam to be pointing. Our Iso-candela pictures, they also have square blocks. Each one of these square blocks happens to be on the 1 degree grid point that Keith was talking about also earlier on. So you can see where each measurement point is. We use our standard color method is a false color, where we show some strange looking colors, but it helps you to distinguish the beam pattern more clearly than if we just showed it as a grayscale image. There are options on the website to be able to change the color scheme, but this is the default color scheme that a lot of you will be already familiar with. And what we're ideally looking for are the brighter colors, blues and pale blues and whites, to be inside the elliptical region, as on the image on the left. The image on the right shows that this brighter area is outside of the ellipse. So when we talk about the measurement points that Keith was looking at, these areas along the bottom are not very brightly illuminated. So you're losing a lot of valuable brightness, which goes to make up your average Iso-candela reading. So this particular one, by looking at this image and looking where the bright spot is, I would say that the particular beam on this side of the fitting is pointing slightly higher than I would expect it to be if the fitting was perfect. So I shall move on, and here we go again. Here's the inner ellipse that is talking about, and here is the 1 degree grid that we're looking for. And again, as Keith was pointing out previously, there is a toe-in angle specified for some fittings like edge lights and or touchdown zone lights. Okay. So this particular example here Then we have the ellipse there, matches this ellipse here. And in this particular instance, there is a toe to one side, which we've moved the ellipse across to the relevant toe angle, which is 3.5 degrees. Okay, this is where we expect the light to be pointing, and in this particular instance, that does appear to be quite correct. With a lot of elevated fittings, what you will find on the top is there is an arrow or some other kind of marking which should be pointing towards the runway center line. When that is the case, then your fitting has the toe left and the toe right pointing so that the beams are shining inwards towards where we expect the pilot to be. If you put it the wrong way round, then these light beams will be focused out into the grass, which is not where we expect the pilot to be, hopefully. Now, with the inset fittings, they still have this toe in, but sometimes you can't see that by looking at the fitting. Specifically with the LED ones, they tend to be a little bit more difficult to discover which way they're actually pointing. But again, usually you will find a little triangular mark or an indentation, or maybe even an arrow sticker somewhere on the fitting to help you to make sure that you install it in the runway in the correct direction, the correct orientation. Okay, so for that runway edge light, that elevated runway edge light, we have one side toe to the right, and we have the other side toe to the left. So as Rob has already pointed out, our reports will show you both sides of the lamp so we can have a look at what that light fitting as a whole is doing, or we can have a look individually at each side. So that gives you a clue by looking at both sides of that, perhaps what to expect when you actually go to physically see that fitting out on the runway. For a typical elevated fitting, it's usually on some kind of frangible fitting, and people come along and they cut the grass and they knock these things, and jet blast comes along, or you'll find an owl decides it wants to sit on it, and so they never normally stay perfectly aligned throughout their entire serviceable life. You have to keep coming along to them and adjusting their orientation and their angles. And I have my glamorous assistant, Lucy, the lighting lady, who's going to help me here. And she's going to do an impression of an elevated light fixture with her arms outstretched to indicate where those beams of light are pointing. She's got her arms outstretched, but also pointing slightly forwards. So she's pretending to be an inset or an elevated edge light. One side toe to the left and one side toe to the right. And she's a perfectly vertical, perfectly aligned light fixture, and the beams are pointing exactly where we would like them to be. Now, there are only a few different scenarios for a light fixture that's elevated that can happen. So if we push Lucy over, so she's leaning backwards, what tends to happen is that makes her arms point further up into the air. And you can see here examples of what happens when you look at the two sides of a same fitting. The brighter part of that beam is now moving up out of the line of the ICAO ellipse. So just by looking at these ICAO Iso-candela pictures, before I even get to a light fitting, I can suggest to the operator, the guy who's going to go out there and do the servicing, that perhaps he needs to make sure he's got some tools on the van so he can change the alignment and make this light fixture more upright. Okay. Here's an example of Lucy, and she's got the arrow on her head pointing the wrong way, so her light beams are pointing out into the grass rather than in towards the runway. And the effect of that is that the bright part of the beam has swapped to the opposite axis on both sides. So I know that Lucy needs to be spun around 180 degrees to make this fitting perfect. Okay, another thing that could happen to Lucy is we could spin her but not 180 degrees. And in this particular instance, what's happened there is that one side has moved more to the straight ahead position, and the other side of the light fitting has towed more than it should be. And so there I can see that what we need to do is we need to twist Lucy round 3.5 degrees to move this into the straight ahead position. The other thing that can happen to Lucy is she can be knocked over sideways. And if that happens, what tends to happen is one of the light beams will begin pointing down towards the ground and the other one will be pointing up towards the sky. And you can see here, the brighter part of this beam, it's also slightly straightened, which means that she's been twisted as well, but it's lower to the ground. And on the other side, the brighter part of the beam is higher up. So again, by looking at these two diagrams, I can suggest that we need to align this fitting and we need to straighten it up. Okay, so again, if she tilts over a bit the other way, we see the difference is that this beam goes up and this beam comes down. So if we have rubber deposits or other problems which are causing low light output, our false color image gets very dark. The darker pictures start to show me that there's something wrong with the light output. Now, that could be, as in this instance, because we have rubber on the lens and that's stopping the light from coming out. But it could also indicate that there's some kind of internal fault, electrical issue, or that there's the blackening of the lamp or whatever. All I can suggest from looking at the Iso-candela is that there is something wrong with this particular location and we would need to go there to actually diagnose what that fault is. Okay, for inset fittings, a lot of these alignment issues go away because it's in the ground, it's bolted in the ground. As long as the can is correctly installed and correctly aligned, then in theory, all of the light beams should point to the correct part of the sky. But what sometimes happens, and more so with halogen fittings than with LED fittings, but it can happen, is one side of the fitting can be reasonably good and the other side can be out of alignment. With a halogen fitting, that could just be something simple like when somebody refurbished the light, that the new dichroic lamp was placed in the holder but wasn't quite square in the holder, so it's actually pointing in the wrong direction. I have actually seen personally examples of where the lamp itself, the reflector has cracked, and that can cause something very similar to this. Or, believe it or not, even putting the lamp in the wrong way round, they usually have an arrow which says up. If you put that in at the wrong angle, then you can actually affect where that beam shines. The lamp is designed in such a way that the filament is designed to hang in a certain place, and then the light will come out of the fitting in the correct orientation on the sky. So if you're looking at an Iso-candela picture and it's completely dark like this, probably in all possibility, you'll find that when we go to have a look at the fitting on the runway, that indeed the fitting is out and we need to either replace that fitting with one that's serviceable, or if we try that and it still doesn't light, then we have obviously got some kind of electrical issue which we need to investigate in more detail. So that was a very, very quick overview of how we look at the Iso-candela pictures. And that set of little slides there will give you very many cues as to how to interpret those diagrams that you get by looking at the MALMS dashboard and by looking at these Iso-candela charts that Rob was talking about. And at that, I shall pass the presentation back across to Rob.
Thank you, Paul. Okay, so earlier I spoke about the Iso-candela diagrams having a history over multiple pages. We always show, after a survey, we always show results of both sides and underneath the previous survey so that you've got that to compare with. But over multiple pages, we form a history of all the surveys of a particular lamp. And there's a link on that report which opens up a line graph report, so we can see both sides of the lamp there in blue and green. And over, I think this graph is over a 5-year period, we can see how the performance of the percentage of standard drops and comes back up. Over time, we can see when it dips down under the 50%, And this allows us to estimate how often will a light need cleaning, or even long term, how often will a light need replacing. So you can plan your differential maintenance. And if we bring MALMS engineering into play as well, where we record when lamps are changed and cleaned, we can mark these on this graph too, and we'll see this a little bit later. We can really start to predict how often things need cleaning and replacing. So next slide, please. Okay, so another view of the photometric data is on our map. So here we're showing the course bar chart information in the familiar colours of green, blue and red, but geographically, so you can actually see where the reds and the blues are. So I'm showing this in comparison with a course bar chart. So we're looking at the that edge along the top. So this course bar chart is in reverse order as the pilot would see the lamps. So we can see that third lamp along is red. Yet another tool to help you visualize where your issues are. And also here on the map, we can see the red, the lamp opposite is red as well. So that may indicate some problem on the runway there. Okay, so next slide, please. Okay, so now we're moving into MALMS Engineer, which is another tool we have for looking at serviceability and compliance. So in MALMS Engineer, we're talking about assets now. So an AGL within the MALMS Engineer system is both sides of the lamp. So it's in two separate runways. And now we divide the runway up into areas and zones, which is configurable. So that is, you plan that however you want within for your specific airfield. So in terms of serviceability in MALMS Engineer, we can look at it in two ways. First of all, we can look at number of faults outstanding by area, but also we can look at the percentage of assets which are currently serviceable. And on the dashboard, we show these metrics along with these warning badges. So for fault status, we have a warning badge which shows us the number of faults which are over 30 days old. So these are the ones that may need addressing quickly. On the asset status side, on serviceability, we have a warning shriek on the badge. This shows us a warning when the serviceability level drops below 95% for a particular area of the runway. So this is one that you need to really get into and investigate. Okay, next slide, please. So if we drill down from the dashboard, we can drill down into areas and then into zones. So we start looking at bar charts. And as I said, the areas which are below 95% are in a warning condition. So we show these in red. So you click and drill down again into zones, and then you can see which zones are in low serviceability. And if you clicked again, you click down into individual assets in that zone as tabular data. So we're not just talking about photometric faults here. We also include our MALMS Engineer inspections, visual inspections. So there might be lights reported out on those. There might be electrical faults, physical faults with the lamp. So all those things all come together with the serviceability. So next slide, please. So if we're looking at an individual asset within MALMS Engineer, we have a report called Asset Information, which is a complete audit trail for that asset. So it gives us some information about the asset, where it is, what area zone it's in, what runway it's on, that sort of thing. Then it shows us the current status of it, its current serviceability. Is it serviceable? If it's not, why? Has it been cleaned? When and by who? Has it been torqued? And has it been photometrically tested on both sides? And what were the results achieved? We show the last 10 faults for that asset and some recent torque information. This is only the first page of the report. So if I can have the next slide, please. So on subsequent pages, we're showing even more information. We've got the course bar charts from the last two, the the last survey on either side, and the latest Iso-candela information. Then on the next page, we show the photometric performance graph, which I've already shown you, but we combine that with the cleaning and repair replace information, which you'll see along the x-axis there as little boxes, little points. So if you see a purple point there, you'd expect after your next photometric test a big improvement. And all this information, including the photometric results, are all shown in a log, which starts here and then carries on over subsequent pages. Next slide, please. So another thing we can do with the map in MALMS Engineer, we can pinpoint areas which have multiple failures over time using a heat map. So we can show the AGLs from white to yellow through oranges and red for 10 or more faults over a period. And we can pick up on hotspots on the runway, which might indicate circuit faults or lamps which need particular more attention over time. That's on a lead on or in the TDZ area. Next slide, please. This is a new report which we've been developing. It's called Survey History, and it shows compliance over a 12 survey period, which if you survey once a month, would be a year. So here we show results for each lamp over the 12 surveys. So you've got the most recent survey on the left-hand side. And for each lamp, we show the percentage of standard achieved, along with the colour, which is your green, blue or red, which you're used to on the course bar charts. So you can instantly see over time how a lamp has been performing, along with all its other colleagues in that course. So on the left-hand side, we have an average percentage standard, which we also colour code. Then we have two form factors. We have the maintenance count, which is the number of times that lamp has been below 70% during this 12 survey period. And then a recent count as well, which is the number of times it's failed recently since it was last good. So we can use these metrics to plan maintenance and hit lamps which may be continual offenders. So if you look at these results here, we show a clean during this period in between two surveys. Maybe you do a survey, you clean, then you do another survey. So we can see there in March we had almost all lights red, and this is actually a piece of centerline which is in the TDZ area, so it's particularly interesting. So we've got very poor results before the clean, then afterwards a noticeable improvement. Then we start to look at some lights which maybe haven't been improved by the clean, and we change those, and that's shown with the pink box. So again, we've got a couple there, about the 4 which are improved following a replace. So yet another tool which is very helpful in planning your maintenance, and if you use that, then you could achieve this sort of improvement. I'm going to hand back to Robert now. Oh, sorry, to Keith now.
Oh, hi. Hello. Thank you very much, guys. I think it's pretty clear that, you know, if you have an asset management tool, such as the MALMS Engineer, and the MALMS Engineer is the most effective one in the marketplace, and I can safely say that. And but the real issue is that we need to be able to service our customer, and our customer is the pilot, the airport, the regulatory body, etc., and the airlines themselves, because the key issue is that the lights must work upon demand. Then it must be worked in a compliant manner. And ultimately, whilst we are servicing our customers, we're doing it to ensure that there's safety and there is compliance. So for pilots, I mean, they get the best visual cues when they need them, upon demand in low visibility conditions. The airport operator themselves, they're the owners, they're maximising their facility, because the airfield is an asset to them. And the airlines, well, if you're coming and flying, from Istanbul, and you're flying into where I come from, say London Heathrow, then the last thing you want is to arrive at London Heathrow and say, "Oh no, can't take you at the moment. Would you go in the stack?" For example, So or even divert. And once you start to divert, then you put aircraft in the wrong location. We've got air crew in the wrong location. They run out of hours and all things like that. So the key issue for us is that we really are servicing the end customer, but in the most effective analytic way that we can. And by using differential maintenance techniques, call it what you like, condition-based maintenance, performance-based maintenance, but using the tools that are available to you today, then you can demonstrate safety and demonstrate compliance. And I know, looking at some of the participants around the world, Kybert in Turkey, hi Kybert, and Cataligo down in Johannesburg in South Africa, hi, and Charlie in Singapore, hi Charlie. So, it's really good. And Steve Hutton in the Middle East, you're online, I see. So, it's hi to all of us around the world, but we've all got the same issues, haven't we? We need AGL performance, safety, compliance, as simple as that. So now we'll go on to some of the questions, I think, Robert, shall we?
Yes, Keith, thank you very much for that. Excellent presentation as ever. First of all, I just want to point out that before we start off, that because some of you may be running short of time, next week we have a very informative presentation on AGL design methodology. This webinar will discuss and provide an explanation of how in practice an AGL designer goes about implementing the ICAO military and or national regulations, plus the practical methods used in AGL design, in the AGL design process to achieve compliant AGL and ground traffic management systems. So as you understand the thinking that goes into the design of the systems that we have to maintain. So we're very proud to advise that John Laheath, specialist AGL designer, and Keith will be hosting that presentation, or this next week's webinar, which will be interactive as ever, and we'll be answering your questions and answers. In fact, we even have some questions already concerning this area. So, and the following week we'll be looking at AGL cleaning, an AGL cleaning case study, particularly interesting because I see we have a couple of questions on that for today. But we'll move on quickly to the questions. If I can go to the panel now, we have the panel view there. The first question, I'll bring in Tony, who's been sitting there very, very patiently. We have some questions regarding the topic of signage in particular. And one question says, should in-service monitoring be carried out on all types of AGL equipment? For example, should approach lights and signs be tested? And then I have Sekar from Sekar has asked, could we describe the procedures of chromaticity measurements of taxiway guidance boards? And also, what would the passing range of what are the how do you measure, what are the pass rates? I see we're talking about candela here. It's actually measured in terms of lux, because it's illuminance of the signs we're actually measuring. Could you share a bit of your knowledge on signs and the need to measure them, Tony?
Yeah, we've spent a lot of time in these webinars really focusing on the runway lighting and the approach lighting for the runway. Absolutely key, of course, but we have to remember that an aircraft flight is say chock to chock, from when you push back until you arrive at the destination. and come into the stand. And so the runway, both in departure and arrival, is crucial, but you've got the ground movement side, which is also crucial. If you're going to maintain movement rates, you want the aircraft to be able to leave the runways expeditiously or go onto the runway expeditiously and safely. And when they're in the taxiway system, to be able to navigate from the runway or back to the runway for a takeoff. And so signage, for example, is very important in that. And in the visual aids panel about 25 years ago, we put a lot of effort into designing a signage system that was conspicuous, legible, credible, and comprehensible, so that pilots could find their way around unambiguously, because it was clear that that's a very important part of safety, certainly. Unintended runway incursions, an obvious danger, but also the unfortunate thing if pilots take the wrong turning in the taxiway system and then cause a lot of trouble rearranging themselves to go to the right place. So signage has to be easily understood and interpreted. And prior to that work, different countries had different colors for signs, different wording on them, different pictograms. And what is in Annex 14 now is a result of a fairly comprehensive piece of work, both as to what information you're going to put on there, otherwise what was credible and comprehensible, but also legibility, the signs, the size of the signs, the colors of the signs from the conspicuity as well. Signs that to do with safety, signs that to do with the way you navigate. So basically red signs or yellow signs. And the taxiways, when they are more than just a simple taxi in, taxi out the ends of the runway. Complex airports like Heathrow, Atlanta in the state, a lot of places with a very complex taxiway system, and pilots are told what their route is to follow, but unless the signs are readily understandable, pilots will have to stop or indeed make the wrong thing. So the whole of that package means that pilots can taxi at the speed they want to taxi at and not go lost, get wrong. And after we introduced this, about 2 years after we introduced this worldwide, one pilot came to me and said, well, for the first time, I don't get lost when I'm taxiing around now. I've got this new signage system. And a former test pilot of mine who then was flying in the airlines, I said, to him one day, what's the thing that gets your adrenaline going most in a whole of a flight? He said, it's the taxi in to an airport that I'm not familiar with, where I can so easily get lost, or I might so easily get onto an active runway. So signage, meeting those specifications, that can be seen soon enough, the pilot can interpret the information, understand it, is absolutely crucial. So again, monitoring leading to good servicing is absolutely vital for all of the signage systems.
Right. Thank you for that. Yes, we've been testing a lot of signs in the recent past, and it's been quite interesting that frankly they are often, because they're on, they are neglected, other than when the lamps go out altogether. And what we're finding is, particularly on the older signs, not only are there issues with the internal workings of those signs, but the actual condition of the illuminant fascia, the fascia of the sign has deteriorated because of osmosis from the effects of the sun, wind and rain. They're often just plain dirty, and we have a lot of bird nests because birds seem to like to sit on nice warm signs. And in particular, we can sometimes see very long grass and plants growing in front of them. So the signage is generally, I have to say, appears quite neglected in a lot of airports. Then when those signs are replaced, the new LED signs are excellent, but you have to be careful that they're actually conformant, because the rules are quite prescriptive. Firstly, you have to get the correct intensity of the different colours, and the intensities will vary according to the category of operation of your airport. The figures are available in Annex 14. And then also there has to be a consistency of light output. So the ratio of the measurements of one area of the sign to the adjacent area, and as well as the overall comparability of the light is a pass-fail criteria for measurement of sign. So particularly a lot of signs fail because the corners are not properly illuminated. But we can answer you specifically, if you have any issues on those points. So much for signage. Asoka, welcome to you from Sri Lanka, and Bandranayaka, has asked us about cleaning his lights. How often should we clean runway lights, and what cleaning method is most effective? What will be the recommended chemicals or solutions to be used for the inset light cleaning without damaging them? Paul, perhaps you'd like to answer this question.
Yeah, I've seen lots of different methods for cleaning lights, but generally speaking, they tend to be a man with either a paper or a dirty rag and a spray bottle with water, maybe washing up liquid, or some kind of domestic window cleaning apparatus. All of these methods work to a degree, but they all have their own problems. They have problems with obviously manpower having to bend and stoop, and if they're using chemicals, so you've got chemicals on your hands, etc. We have a system which we recommend that you use also, which uses compressed air and sodium bicarbonate. Sodium bicarbonate, you would probably realize, some of you, that it's used in baking as a raising agent. We actually use a granular form of that in order to clean the fittings. It's a very light, mild abrasive, and it's very, very effective at cleaning rubber off of surfaces, but it will not damage rubber gaskets or the aluminium alloys used in AGL fixtures. It's very, very similar technology that people use to restore very old car bodies, and they can strip the paint off of an old car body using this technique, but it won't blow holes in where there's rusty parts of the body. So it's a very, very gentle but very, very effective methodology. And because it's effectively sodium bicarbonate, it's what we use in baking, so it's not detrimental to human health. It's almost pH neutral, so it's not very damaging to the environment. And I believe after it's been in the environment for a while and it's become damp, there's a chemical change and it just basically disintegrates into nothingness. So we would recommend that. And obviously coming up, we've got the AGL cleaning case study. So stay tuned for that one.
Good. Thank you, Paul. Keith, I have a question here. What should the photometric output compliance standard be for light fixtures after servicing in the workshop and before they're reused in the airfield? Is it 100% or something else?
Well, that's a very challenging question, that really, because you think about it. If you're going to go out into the field and you identify that a light unit, let's take a touchdown zone light. A touchdown zone light being an inset light that must achieve a minimum of 50%, but we start to do maintenance at 70%, that it needs maintenance. So that's the criteria, 70%. And so we take it to the workshop, we dismantle the light fixture and do what we can, clean it, check it, and then sensibly would be to have a workshop photometric tester, and because you'll have checked it electrically for electrical safety, we would have already checked for water tightness when you've reassembled it, etc. But many airports do not then think, oh, I've serviced it now, I can go back in the field. But does it really work? So the criteria I'm suggesting should be as near as practicable back to the 100%. Now, clearly, over time, material deteriorates, and I would suggest you'll probably never get back up to 100%. Although lights are designed to give you more than 100% for a variety of reasons, and one is component manufacture in reasons, the tolerances associated with that. Others are installation tolerances, etc. But if you could near as practicably get it back to 100%, that would be ideal. But you have to make a local decision on that, because if you only, for example, test it and you say, oh, it's 85%, I can put it back in the field. Yeah, you can. But next week, you'll be bringing it back in. So the cycle, you're going to cost money, you know. So to have a more stringent workshop testing regime is very, very important when it comes to access and ultimately maintenance costs.
I think the key thing there, Keith, is as you've touched on, you've brought the fitting into the workshop, you've taken it apart for whatever reason. Now is the time to have a look at all of the components that make up that asset and say, well, okay, this lens looks like it's had a pretty hard life. It needs probably to be changed. Let's do it while we have it in the workshop.
Correct.
Make this fitting
100%. Paul, 100%. Right?
Thank you,
a
Keith.
good effective maintenance, workshop maintenance regime will do that, won't they?
Yes.
Thank you, Keith. Mr. Chan would like to know how we do photometric tests for approach lights. I'll take this one. I mean, we have tried all with the photometric testing equipment we can measure lights up to 1 meter elevation with the transverse or in a line individually. Alternatively, if they're above a meter, we have equipment. We have equipment that can be raised up easily on a cherry picker, as we call it, a lift, so we can do the photometric measurements for according to the method specified in ICAO for individual lights. It does take longer, but it can be done. We have tried drone methods, but photometric measurement is not yet feasible with a drone. You can take a picture of the lights, but it won't get a photometric measurement according to ICAO with that. So it's a combination for the low-level lights with the photometric testing equipment used for measuring the runways up to 1 meter. Above that, it's actually using the Sine and Papi tester. Of course, these lights can, of course, be measured on the laboratory tester. But remember that in ICAO it specifies that the photometric testing is only required for the first 400 meters where they're accessible. So moving on then to Rob, you think you may have got off lightly so far. We have a question here from Mohammed, who would like to know in MALMS reports, if he wants to look at the serviceability of a specific light, it's actually talking about a Cat 2 light, runway light, but I don't think it matters which light it is. Within MALMS, how can you see the performance of a serviceability report for a particular light over a period of time, please, Rob?
Yeah, there's 2 places you can get to this. From the Iso-candela report, when you've got multiple pages showing a history, there's a link in the bottom right corner of the report, takes you to the performance graph. Alternatively, from the map, you can click on an asset on the map view and you'll see 3 buttons, which are very useful. The first one is a bar chart, takes you straight to a coarse bar chart containing that lamp. There's a light bulb button that takes you to Iso-candelas, and you'll see a little line graph button, takes you to the photometric performance line graph for that light.
Thank you, Rob. If you have anybody has any specific MALMS questions, please email us, and we'll of course be only too happy to answer them for you. One for you, Tony, here. Annex 14 requires average intensities inside the inner ellipse of the relevant Iso-candela diagrams of 20,000 candela for approach lights, 10,000 candelas for runway edge lights, and 5,000 candela for runway centerline lights. Why are the intensities not the same for all lights?
Well, basically, I think the best way of answering that is to explain very briefly the design criteria behind this set of lights. This fundamental requirement, an aircraft approaching the runway, the pilot at some point, hopefully, will see some approach lighting. Once he sees that approach, or she sees that approach lighting, sees what I call a segment, a number of lights, part of the total pattern. Unless it's an automatic landing, at some point the pilot has to make a decision whether he has enough visual references to continue to a landing, and that may involve, particularly in Category 1, a significant lateral manoeuvre to get to the runway centre line. That's sometimes forgotten, that you don't necessarily come out of the fog, the low cloud, lined up with the runway. You may have to manoeuvre, and so you need a certain number of lights. It's often said, oh, you must see at least 5 approach centerline lights and a crossbar before you can make a decision. But the point is, having got that the picture, you want to retain at least that amount of point view, and normally you'd expect it to increase as you get to the runway. What you don't want is, because it can be dangerous, is the lighting not to be properly matched all the way down as you go from approach to runway edge to centerline, where as you go from one type of light to another, the amount of lighting you can see, how far you can see, reduces, because that potentially, and it has happened, caused accidents, pilots see less lighting suddenly in front of them. They think, therefore, the aircraft is pitching nose up, so they pitch nose down. They're in danger of flying the airplane into the undershoot. So these intensities were carefully selected such that you've got this smooth transition. There's also the practicability factor comes in. Really, certainly in the early days when this was designed, to get more than 5,000 candelas out of an inset light was extremely difficult. To get that amount of light flux out of a small hole was difficult. So that, in a sense, sets the lower value. Then as you go to the edge lights, there's more beam spread required. You've got a limited amount of flux, but you can go to a higher wattage, and so you can say 10,000. That will give us a wider beam spread as well, but also match the center line. And similar the approach. So as you come in, you're not looking at the peak of the beam all the time. You're looking at we stressed earlier in these webinars, the whole of those beam spreads are used at various points during your approach. And so if you look at it, and it's difficult just to talk about it, but if you actually look at it, it is a seamless transition from the highest intensities, which give you the best chance of making contact on the approach, to levels that are adequate on the runway. You don't want too much light. You could start to get into glare problems well, at night, when you want the maximum amount of light to penetrate. If you're not careful on the runway, you could have a runway centerline light, which was giving you discomforting glare at the least, if not disabling. So it's a match system, and it was found, a lot of experimental work, that these 3 values meant that you didn't go from one to another with a sudden change of what you could see.
Good, thank you, Tony. I think it's always good to be able to understand the reasons for the standards that we comply with in context. And Tony, of course, was very much part of the standard setting process for those standards that are now our task to achieve on a day-by-day basis.
Can I just say one other thing about that? We've got these ratios, 5,000 to 10,000, that's 2 to 1, 10,000 to 20,000, 2 to 1. It is a mistake to say, oh, I can make some much brighter approach lights. I can have 40,000 candela approach lights. Yes, you would get earlier visual contact, but then if you get down to the runway and you've got more than this 2 to 1 intensity change, you'll get into this, it's often described the black hole effect, where suddenly you think you're losing visual references. Well, you are, but it can be, in a dynamic situation, quite unsettling for the pilot and may cause him to mishandle the aeroplane. So if you're going to have 40,000 candela approach lights, you need to have 20,000 edge lights and 10,000 centerline lights. So you don't go to one manufacturer because he can produce beautiful high intensity approach lights and go to somebody else for your runway centerline. You need a match system all the way through.
Yeah, so for those that want to see more information on this, look at the collective notes to figures A2.1 to 2.11 and 2.26 in Annex 14, Volume 1, and that explains these ratios in more detail.
That's at the end of the Iso-candela diagram section.
That's correct, Tony. So very, very interesting. So thank you. We'll move on just a couple more because we're over time, as unfortunate as usual. Mr. Narayanan has asked how to check photometric tests for PAPI lights. How do you check a PAPI light, Tony?
How do you check it? Well,
yes.
Until relatively recently, it was very difficult. But now, of course, as last week and the week before, it showed the device that TMS have developed, where this device put in front of the PAPI unit can measure all the essential parameters. The Iso-candela diagram, that the beam spread is correct, that the colors are compliant with the required colors, and also that there's a sharp transition between the red and the white sector, and also that transition is at the right elevation angle for that particular setting. But until we've had this equipment, and it's the only one I know that offers this sort of service, we've had to rely very largely on people using inclinometers and assuming, having to trust that everything about the internal optics is as it should be, and therefore if they put the inclinometer on the plate at the side and set the angle, that's the correct angle, and then rely on a flight test where a pilot can actually exercise the guidance in the sense of going up and down in the beams and seeing that the lights change in the right sequence, and get some impression of whether if he goes through the lights, say flying level, the time interval between each click over is approximately the same. But that, if you like, is a functionality. It's not really a calibration. What we now have got for the first time is a calibrating device, and it's a big step forward.
So thank you, Mr. Narayanan, for that question. It's very welcome, as you can appreciate, and I'll happily send you a brochure. Right, now we really are running over time. All these questions will be answered, and the answers posted on our website. This is week 9 of the TMS Tuesday. The last question for you, Keith. This is an anonymous question, but a very interesting question that you may know the answer to. I'm sure you do. We've recently installed LED lights and noticed some lights randomly flashing. What could be causing this? Keith? You're on mute, Keith. Keith?
You can hear me now? Yes.
Yes, we can.
Yes, you can. It depends on which, which power unit. If they've just replaced tungsten halogen with LEDs and they still have a thyristor-based CCR, then of course they'd have to be tapped down. The CCR needs to be tapped down, so that could be a factor. It is more likely, though, because of they moving to LEDs, it's probably the fact that if they've done a complete package, that is the CCR and the LEDs, because on low harmonic regulators, then and they've got the modern LED fixtures, which perhaps have the smart units, and I don't know which model that they have. So if they've got the smart units, which have got individual light control and monitoring then built in, then there's some differing technologies, pulse width modulation technologies, PWM, and anybody wants to learn about PWM, maybe you go to Wikipedia, because I tell you it's quite a subject. But a mismatch of technologies can create this, and particularly when we're looking at LEDs, and this conversion to LEDs is at the lower intensities. So it's more pronounced at the lower intensities than it is at the 6.6 amps.
Right, thank you. Thank you for that, Keith. Look, I'd love to go on, but I know you've all got work to do. But I'd like to thank everybody. I'd like to thank our presenters, Keith, Tony, Rob, and Paul, for their contributions today. I'd like to thank the back office team who've helped put this all together. And I'd like, most importantly of all, to thank you participants, without which we wouldn't be holding this, this webinar. So thank you very much for your participation. As I said, next week, we'll be looking at design and design methodology. We have a we have an actual designer who will be telling us about how they do their work, what's important to them, what the challenges are, how they solve those, and why they do what they do, which I think will be very interesting for us as airfield lighting professionals. So I'd like to thank you all very much, and see you all at the same time, same place next week. Good afternoon, or good morning, or good night, wherever you are. Bye-bye.